Well, thank you, Allure, for the nice introduction. And it's a great honor and somewhat nostalgic for me to give a talk at POPL because, as Allure mentioned, I presented the first paper at the first POPL conference in 1973 with Steve Johnson and Jeff Ullman. I'll describe what was in that paper shortly. The thesis of my talk today is that the two pillars of computational thinking, abstractions and algorithms, have transformed the field of compiler design from an art to a science. Computational thinking is one of the hottest areas in STEM education circles today. It got a big boost from a paper Jeanette Wing published in the Communications of the ACM in 2006, in which she stated that computational thinking should be taught, along with the 3 R's, to every school child. But as important as computational thinking is, the irony is that there isn't a standard definition for computational thinking in educational circles yet. However, the definition that I like the most is that computational thinking is centered around the thought processes involved in formulating problems using abstractions, so their solutions can be represented as computational steps and algorithms. I like this definition because the POPL conferences, since their inceptions, have played a major role in presenting many of the key abstractions and algorithms that have transformed the field of compiler design from an art to a science. And I'll mention just 2 such papers from the very first POPL conference in my talk today. A good place to begin is to try to define the term abstraction. This is actually very hard because virtually every area of human endeavor uses distinct abstractions to describe what that field is about. As a consequence, there is no standard definition across different fields for the term abstraction. For example, compare the abstractions used to describe chemistry with the abstractions used to describe music. A musician's abstractions get no reactions from a chemist. In our Turing Award paper, Jeff Ullman and I defined an abstraction as a mathematical model with 2 components, a data model and a set of operations. What distinguishes this definition from abstractions in many other fields is that in addition to a data model, our definition of an abstraction has an associated set of operations for manipulating the data in the model. The operations can be thought of as some kind of programming language, which need not be Turing complete. A simple example should clarify this definition. Consider the dictionary abstraction in computer science. It has a data model consisting of a universal set U of elements and a subset S of U, which is initially empty. The programming language consists of straight line sequences of 3 instructions. Insert an element into X, delete an element from S, and look to see if a given element is in S. A dictionary is a good abstraction for what you do with a symbol table in a compiler. We are all familiar with the notion of an algorithm in computer science. Informally, I like to think of an algorithm as just a recipe for doing something. Formally, we can define an algorithm to be a Turing machine that halts on all inputs. I might mention there are some people who say an algorithm does not have to halt on all inputs. But when I, John Hopcroft, and Jeff Ullman wrote the Design and Analysis of Computer Algorithms book in 1974, we checked with Don Knuth, who the New York Times later described as the Yoda of Silicon Valley. And he said, an algorithm must halt on all inputs. In our algorithms book, we call the Turing machine that need not halt on all inputs a procedure. This algorithm procedure distinction is analogous to the distinction between total recursive functions and partial recursive functions in recursive function theory. In our Turing Award paper, Jeff and I define a rudimentary taxonomy for computer science abstractions based on their purpose. For starters, we included 4 categories in our taxonomy: fundamental abstractions, abstract implementations, declarative abstractions, and computational abstractions. However, we feel there are many other categories that can be added to this taxonomy. Our first category, the fundamental abstractions, include those that are usually studied in a first course in computer science. Common examples are dictionaries, stacks, queues, graphs, and trees, and also classes and their methods, but the methods are without specification. Our second category we called abstract implementations. These are data structures that are useful for implementing fundamental abstractions. Common examples include hash tables and various kinds of search trees. Our third category we called declarative abstractions. They are higher level abstractions like regular expressions, context-free grammars, flow graphs that specify what we want, but without specifying how to do it. They need not be Turing complete, and as we shall see, many of these declarative abstractions are routinely used in compiler design. Our fourth category we called computational abstractions. These abstractions more closely model actual machines and programming languages, and they are Turing complete. Other computational abstractions of this nature are Turing machines, Boolean circuits, and quantum circuits, which I will discuss in the last part of my talk. An important property of abstractions is that they can be layered, and they can be implemented by algorithms or in terms of other abstractions. For example, the dictionary abstraction can be implemented using a linked list abstraction. As we shall see, this layering process allows us to impute a running time for an abstraction. For the remainder of my talk, I will use the term compiler to mean a program that translates a source program into a semantically equivalent target program. A significant contribution to compiler design occurred in the 1960s and 70s when we started picturing a compiler as a composition of phases that translated the source program into a sequence of semantically equivalent lower-level representations from which the target program is finally generated. The phases shown in violet in this slide are called the front end of the compiler, and the phases in blue, the back end. The modern compiler framework, LLVM, allows one of several different front ends to translate a programming language into a single intermediate representation called LLVM-IR. The front end is followed by a code optimizer that transforms the intermediate representation into a version from which a better target program can be produced by any one of several different target language code generators that can be used in the back end. Each of the phases of a compiler uses distinctive abstractions. I will now describe in more detail how 3 widely used declarative abstractions, namely regular expressions, context-free grammars, and flow graphs, are used in compiler design. Let's begin by looking at regular expressions as a declarative abstraction for lexical analysis. The data model of the regular expression abstraction is sets of strings over some alphabet. The operations of the abstraction are union, concatenation, and Kleene closure on sets of strings. Regular expressions were invented by Stephen Kleene in 1951, and they are now routinely used in a variety of forms in many string pattern matching programs and languages, such as grep, awk, lex, and perl, to mention a few. There are several different algorithms for implementing regular expression pattern matchers with wildly different running times. In the late 1960s, Ken Thompson at Bell Labs used a just-in-time simulation of a non-deterministic finite automaton in his QED and grep programs to search for regular expression patterns in an input string in time that is linear in the product of the length of the regular expression times the length of the input string. In the 1970s, I created a regular expression search program on Unix called egrep that used a dynamic lazy construction of DFA transitions to recognize regular expression patterns. And its observed running time was linear in the sum of the length of the regular expression plus the length of the input string. Also in the 1970s, Michael Lesk and Eric Schmidt implemented a lexical analyzer generator called Lex at Bell Labs. It would take a specification of a lexical analyzer and automatically construct a lexer from it. Lex used regular expressions to specify the syntax of tokens, and Eric Schmidt, as a young intern at Bell Labs, put one of my fast regular expression pattern matching algorithms into Lex. As you may know, Eric Schmidt, when he grew up, became chairman of Google. Lex is a tool that allows users to create efficient lexical analyzers from regular expression-based specifications without having to learn an algorithm for efficient regular expression pattern matching. Here is a simple example of a Lex specification for recognizing integer numbers. Fed into Lex, this specification produces a lexer that would recognize a sequence of one or more digits as an input. Install the sequence of digits into a symbol table and return as output the token num along with a pointer to the sequence of digits in the symbol table. Lex and its descendants like Flex on Linux are still used today to build lexical analyzers, almost 5 decades after the first Lex tool was created. Let's now consider the next phase of the compiler, the syntax analyzer, or parser as it is often called. The declarative abstraction of context-free grammars is routinely used for specifying the grammatical structure of programming languages. Surprisingly, the idea of a context-free grammar is old. It gets attributed to an Indian scholar named Panini, who used a context-free grammar somewhere between 400 BC and 200 BC to specify the syntax of Sanskrit. Various forms of context-free grammars are used today to specify the syntactic structure of programming languages. In 1973, I presented a paper with Steve Johnson and Jeff Ullman at the first POPL conference, in which we introduced a formalism inspired by Knuth's LRK grammars. The formalism used a syntax-directed translation scheme with semantic actions attached to the productions of a context-free grammar for translating a token stream into some kind of output, usually a syntax tree. The productions of the context-free grammar would be augmented with disambiguating rules. The grammar with the added rules could be used to parse an input string unambiguously using a deterministic shift-reduce parser. Steve Johnson, Jeff Ullman, and I described such a parsing algorithm in our 1973 POPL paper. At the same time, Steve Johnson implemented a software tool called YAC at Bell Labs for constructing efficient syntax analyzers from these kinds of formalisms. YAC allowed compiler designers to write simple grammatical specifications for programming languages without having to learn the details of the algorithm for constructing the parser for them. YAC and its descendants, like Bison, are still widely used for creating parsers. I might mention it was Jeff Ullman who coined the term YAC. It stood for Yet Another Compiler. Lex and YAC can be used together to create the front end of a compiler. Here is a YAC specification for a desk calculator that evaluates arithmetic expressions involving the addition and multiplication of numbers. Compiling this YAC specification with the lexical analyzer created from the previous Lex specification for integer numbers, we get a working desk calculator. The combination of Lex and YAC allowed people to experiment with the syntax of programming languages, and Lex and YAC became very popular in compiler courses for that purpose. Let us now look at flow graphs, an important abstraction that is often used in the code optimization phase of a compiler. Flow graphs can be used to model the flow of control in computer programs. At the first 1973 POPL conference, Gary Kildall presented a paper in which he showed how flow graphs could be used to facilitate the implementation of useful code optimizations on the intermediate representation of programs by computing reaching definitions. A few basics. Suppose we have a three-address statement S in our intermediate representation, like U is assigned V plus W. We say this statement generates a definition of the variable U. We say a definition of U from statement S reaches a statement T if there's an execution path from S to T where the variable U is not redefined. In the parlance of code optimization, we say it's not killed. The reaching definitions problem is to determine what definitions may reach what program points. And reaching definitions are used to implement several important code optimizations, such as constant propagation and loop invariant code motion. Now let's take a look at the flow graph abstraction for reaching definitions. The data model for this abstraction is a semi-lattice of subsets of variable definitions. These are the data flow values. And together with the semi-lattice, there is a directed graph in which each node represents a basic block of the intermediate representation, and the edges indicate which blocks can follow which other blocks. And associated with each node of the graph are two members of the semi-lattice, one for the variable definitions that can reach the beginning of the node, and one for the variable definitions that can reach the end of the node. There are two operations in the flow graph abstraction. The first is a transfer function associated with each node. The transfer function computes the output data flow values associated with the end of the node from the input data flow value. And their second operation is a confluence operator that computes the data flow value associated with the beginning of node from the values of the data flow values at the ends of all its predecessors in the flow graph. And because we're dealing with a semi-lattice, the confluence operator needs to be commutative, associative, and idempotent. Different algorithms can be used to solve for the data flow values at the beginnings and the ends of the nodes. And the beauty of Kildall's formulation is that you can choose the algorithm that's most appropriate for computing the data flow values for the kind of optimizations you're trying to perform. The details of these and many other useful abstractions and their associated algorithms for compiler design are presented in a sequence of books on the principles of compiler design that Jeff and I co-authored in the span of 3 decades. The first book by me and Jeff was published in 1977, and it had 600 pages. The second book in 1986 added Ravi Sethi as a co-author, and it had 800 pages. The third book in 2007 added Monica Lamb as a fourth co-author, and it had 1,000 pages. None of us had the heart to write a fourth book. The books quickly became known as the Dragon books because all the covers had the drawing of a fierce dragon conceived by Jeff, symbolizing the complexity of compiler design. I might mention it was Jeff's youngest son, Scotty, who designed the cover for the Purple Dragon book, the most recent Dragon book. I might also mention that the Red Dragon book was briefly shown in the 1995 movie Hackers, starring a young Angelina Jolie. When my 2 children saw the movie, for the first time, they thought their old man was really something. It shows you what it takes to impress your children these days. The impact of the abstractions and algorithms presented in these books and developed by the field has been substantial. They have transformed the field of compiler design from an art to a science. The first Fortran compiler built by IBM in the 1950s took 18 experienced staff years. In contrast, starting from the mid-1970s on, scores of innovative languages like Brian Kernighan and Lorinda Cherry's EQN language for typesetting equations have been created in just weeks using the tools and abstractions documented in the Dragon books. I might mention that the Kernighan-Cherry formalism of EQN was adopted by Don Knuth in his TeX typesetting system. The books have also been used for decades in universities around the world to teach compilers to generations of computer science students. Let me mention an anecdote about my experience teaching the 1-semester compilers course to thousands of students at Columbia for the last 25 years. In addition to teaching the abstractions and algorithms used in compilers, I had students form teams of 5 for a semester-long project that accompanied the course. Each team had to create an innovative new programming language of their own design and write a compiler for it. Many of the languages created by the students far exceeded my expectations. One memorable language was called Upbeat. With it, users could write programs to play sound of their own choosing to accompany streaming input data. The students who created Upbeat showed off their language by writing a program that would play user-selected music triggered by user-specified patterns in the input data detected by their program. They illustrated their program by taking the New York Stock Exchange ticker tape feed and having their compiled target program play music fitted to the patterns in the ticker tape data. When the market was going up, the music was bouncy and lively. When the market was going down, the music was gloomy and somber. Their theory was that a stockbroker would rather listen to background music that would indicate which way the market was going rather than staring at the ticker tape all day. I might mention Adrian Weller, one of the students on the Upbeat team, was a stockbroker before he came to Columbia as a PhD student. Adrian is now a principal research fellow at the University of Cambridge. I should also mention that in the 25 years that I taught the compilers course at Columbia, never did a team of students fail to deliver a working compiler for their innovative programming languages. I attribute this success to the tools, abstractions, and algorithms that we documented in the Dragon books, and to the software engineering process that I learned working 30 years at Bell Labs. For the last part of my talk, I'd like to mention a few unusual abstractions in quantum programming languages that are vastly different from abstractions appearing in traditional programming languages. The point I'd like to make is that the framework we've created for designing compilers for traditional programming languages can nevertheless be applied equally well to create compilers for quantum programming languages. I will begin by reviewing the four postulates of quantum mechanics, a fundamental theory in physics developed in the early part of the 20th century that describes the physical properties of nature at the scales of atoms and subatomic particles. From these postulates, we can derive the abstraction of quantum circuits, one of the key models of computation underlying quantum programming languages. I'm going to follow the treatment of quantum computation as presented in Nielsen and Chung's classic book, Quantum Computation and Quantum Information. Postulate 1 says that the state of an isolated physical system can be described by a unit vector in a Hilbert space, which is a complex vector space with an inner product. From this postulate, we can derive the notion of a quantum bit called a qubit, which is a unit vector in a two-dimensional Hilbert space. The state of a qubit can be represented by a linear combination of the computational basis states ket0 and ket1, as shown in this slide. The funny brackets surrounding symbols are vectors using the bracket notation that was devised by Paul Dirac, and this bracket notation is standard in quantum mechanics papers these days. The vector ket0 stands for the vector 1, 0, and the vector ket1 stands for the vector 0, 1. And since every vector is a unit vector, the sum of the squares of the absolute values of alpha and beta are equal to 1. A qubit is fundamentally different from a bit in classical computing. It exhibits a quintessential property of quantum mechanics. Its state is a superposition, a complex linear combination of two basis states. Postulate 2 states that the evolution of the state of a closed quantum system can be described by a unitary operator. For the purpose of this talk, you can think of a unitary operator as a complex square matrix whose rows and columns are orthonormal. A unitary operator represents a rotation of the state vector in Hilbert space. Unitary operators are reversible. In contrast, operators in classical programming languages do not have to be reversible. The single qubit Hadamard operator is a useful unitary operator that appears in many quantum algorithms. If we apply the Hadamard operator to the computational basis state ket0, we get the superposition ket0 plus ket1 over the square root of 2. Likewise, if we apply the Hadamard operator to the basis vector ket1, we get the superposition ket0 minus ket1 divided by the square root of 2. And notice that if we apply the Hadamard operator to itself, we get the identity matrix in 2 dimensions. The 2-qubit quantum knot operator, or control knot operator in full, has a matrix representation shown on the right. It is a very useful quantum operator that appears in a number of quantum algorithms. It has 2 qubits, C and T. C is a control qubit and T is the target qubit. And when these 2 qubits are fed into a C0 gate, if the control qubit is 0, the target qubit passes through unchanged. If the control qubit is 1, the target qubit is flipped. So for example, if we put the input with C equal to ket 1 and T equal to ket 0 into the C0 gate, the C0 gate produces ket 1 on the control line as output. That's the control hasn't been changed, but that the target qubit has been flipped from a 0 to a 1. Postulate 3 says the only way to get information out of a quantum system is to measure it. A measurement returns an outcome with some probability. The sum of the probabilities of the possible outcomes of a measurement is 1. And a measurement is not a unitary operator. It collapses the state of a quantum system. As an example, let us consider the projective measurement of a single qubit psi equal to alpha times ket 0 plus beta times ket 1, as shown in this slide. You would like to get the amplitude of psi as an outcome, but in the world of quantum physics, you can only get one classical bit, a 0 or a 1, as outcome. The probability of getting 0 is the absolute value of alpha squared, and the probability of getting 1 is the absolute value of beta squared. Moreover, if the outcome is 0, the state after measurement is ket 0. If the outcome is 1, the state after measurement has collapsed to ket 1. The final postulate says what happens when we combine 2 composite systems. The state space of the composite system is the tensor product of the state spaces of its component systems. Excuse me. I've shown on this slide an example. If we take two-dimensional vectors A and B and take their tensor product, we get a 4-dimensional vector as a result. And if we take the tensor product of the 3 two-dimensional vectors A, B, and C, we get as output an 8-dimensional vector. If we add a single qubit to a quantum system, we double the size of its state space. So this means that if we combine n single qubit systems, we get a composite state system with a state space of dimension 2 to the n by taking the tensor product of the state spaces of the n single qubit systems. Note that if we combine 300 single qubit systems, we get a state space with more dimensions than the number of atoms in the universe. This is why it's so difficult to simulate quantum mechanical systems on a classical computer. We are finally ready to introduce quantum circuits, a key abstraction for quantum computing. Quantum circuits are sometimes called the gate model of quantum computing. Quantum circuits are a little bit like Boolean circuits, but there are important differences. A quantum circuit is an acyclic graph consisting of lines connecting unitary operators and measurement gates. No fan-in is allowed because logical OR is not a unitary operation. Logical OR is not reversible. In addition, no fan-out is possible because in quantum mechanics, it is not possible to make a copy of an unknown quantum state. This follows from the no cloning theorem in quantum mechanics. Here is a simple but important example that illustrates what a quantum circuit looks like. I've shown a quantum circuit with two inputs, X and Y. The X qubit goes into a Hadamard gate, whose output goes into a C0 gate. The Y qubit goes directly in as the target of the C0 gate, and the output is a very funny state. This quantum circuit illustrates how to generate what are called Einstein-Podolsky-Rosen states, also known as Bell states. If we applied ket 0, 0 to this circuit, we would get as output the state ket 0, 0 plus ket 1, 1 over the square root of 2. You can show that we cannot express this output as a product, tensor product of two basis states. States of this nature are called entangled states, and Einstein called these Einstein-Podolsky-Rosen states spooky action at a distance. And you can do some amazing things with entangled states in quantum mechanics. And I might mention that I think almost all physicists don't really understand the phenomenon of entanglement. In 1994, quantum computing received an enormous boost when Peter Shor at Bell Labs published an algorithm combining a classical computer and a quantum computer to factor integers with order n-cubed operations. Many of today's encryption schemes, like RSA on the internet, assume factoring large integers is computationally prohibitive. However, if we could build large enough quantum computers with error correction, encryption schemes like RSA would be easy to crack with Shor's algorithm. But for the time being, no polynomial time algorithm is known for factoring integers on a classical computer, and we cannot build large enough quantum computers to factor the sizes of integers used by RSA in practice. So RSA is safe for now. However, as a precaution, NIST has recently initiated a process to solicit proposals to develop cryptographic systems that are secure against attacks from both quantum and classical computers. I might mention that this is an active research area in cryptography these days. Several companies like Google and IBM have built quantum computers with about 100 qubits, but to implement Shor's algorithm with full fault tolerance and error correction will require 1 million or more qubits. It is not clear when such large-scale quantum computers will become available. From a theoretical point of view, if we could prove factoring integers cannot be done in polynomial time on a classical computer, then Shor's algorithm would disprove the extended Church-Turing thesis, which states that any physically realizable digital system of computation can be efficiently simulated on a Turing machine. Scalable quantum computers are still in their infancy, but our abstractions for modeling compilers for traditional programming languages have been very successful at constructing compilers for quantum programming languages. A little while ago, Christos Foray, a graduate of Princeton University, came to Columbia as a PhD student to study quantum computing. After taking my compilers course, she did her PhD thesis on compilers and design tools for quantum computing. Krista demonstrated that the framework we've created for implementing compilers for classical programming languages can be used to develop compilers for quantum programming languages. After graduating from Columbia, Krista joined Microsoft Research, where she is now General Manager of Quantum Software. A few years ago, she and her colleagues at Microsoft created a quantum programming language called Q# that is now part of Microsoft's Quantum Development Kit, which can be used to experiment with quantum algorithms and design tools. Q# is one of 15 quantum programming languages listed on Wikipedia's quantum programming webpage. In conclusion, I would like to reiterate my thesis that the abstractions and algorithms that we've developed in computer science in the last several decades have transformed the field of compiler design from an art to a science. Thank you.
Hi, Andrew Myers here. I wanted to bring you back to something you mentioned a little bit earlier that for me rouses unexpected passions from PL people, which is LR versus LL.
Yes.
So I guess I'm curious about your thoughts about whether we need the expressive power of our LR, I should say. It seems like in this community, a lot of people have become enamored of using LL for everything. I think the argument I've heard is that it's easier to debug, and people can use things like parser combinators that are kind of cool. So I guess I'm wondering. And I guess the other thing I've noticed is that when I talk to people in industry who build industrial compilers, they tell me, well, we're not actually using parser generators anyway, because we have these parsers that we've kind of curated and maintained for decades, and they're doing all kinds of crazy things that don't quite fit into the easy expression with Yak or Bison or whatever. So I guess I'm curious about your thoughts about this trade-off.
This is an excellent question. First of all, when I entered the field of compiler design back in the late 60s and early 70s, there was a holy war going on parsing techniques. There were many different types of top-down, many types of bottom-up parsing techniques, like simple precedence, mixed strategy precedence, and so on. And then in 1965, Donald Knuth came along and wrote his seminal paper on LRK grammars, where he defined sort of the maximal class of context-free grammars that could be parsed deterministically using a shift-reduce parser. The folks who were building compilers at that time really liked recursive descent parsers. And LL is a prime example of a recursive descent parser. But when I got involved in compilers and programming languages, what I discovered was that in order to write accurate grammars for programming languages, you had to modify your grammar to make it either LL of 1 or simple LR of 1 or look ahead LR of 1 and so on. And many of the people who were writing compilers weren't experts in parsing theory and formal language theory. So they had a great deal of difficulty modifying their grammars to fit the mold. The reason I think Yak became so popular was that the formalism that Steve Johnson, Jeff Ullman, and I devised allowed people to create easy to write grammars for typical programming language constructs. If you had to write an unambiguous grammar, say for if then else statements, this is actually requires a little bit of skill to do this. And with Yak, we created a rule saying that if you have a choice, if you have a shift reduce conflict, always favor for a shift. So that became a simple disambiguating rule where people could use the ambiguous grammar for if then else statements. Likewise, if you take a modern or not so modern these days programming language like C, C has operators, arithmetic operators on 16 different precedence levels. And so if you wanted to write an unambiguous grammar for expressions in C, you'd have to have 16 different syntactic categories to represent the different levels of operators. Whereas if you use an ambiguous grammar of the form expression is expression operator plus expression, all you needed was one rule and a rule that specifies how the precedence and associativity of the operator should go. So the other advantage of using Yak and techniques or parser generators like Yak is that Yak will tell you where the difficult to parse constructs in your grammar are. And when people started using Yak, especially at Bell Labs, they'd always come to me and say, I don't understand why I'm getting this parsing action conflict in Yak. But after I showed them that there was an inherent ambiguity in their grammar, they say, oh, I didn't spot that. So the reason I liked Yak and formalisms at the time is that it resulted in more robust software, more properly working parsers that didn't have any peculiarities in them that many of the handcrafted parsers that people were building at the time. But having said this, if you're experienced in the field, go ahead and use the parsing strategy of your choice. And your comment that some programming language syntaxes are so complex that they require a special organization to create a correct parser for them. And I'm thinking of the language C++ in particular. There is an organization that specializes in the construction of parsers for C++. It's not a task that you would ordinarily want to do from scratch. Another, and this sort of is a biased comment from me, I like theory, and I liked Knuth's dictum that the best theory is motivated by practice and the best practice is motivated by theory. So if you can apply theory to the design of your software, chances are you have more chances of getting a properly working software system. So this is probably much too long of an answer to your question, but the field has evolved considerably from the time that programming languages particularly parsing was a hot area of computer science research. And I might also mention that with the advent of compiler frameworks like GCC and LLVM, the construction of a new compiler has turned into an exercise in software engineering, because to create a new compiler for a new programming language on an existing machine, all you do is construct a new front end and have put it into LLVM, and have your front end translated into LLVM IR. And then you can use the existing target code generator as your back end of the compiler. And likewise, if you want to create a compiler for an existing language for a new machine architecture, all you then have to do is create a LLVM IR to target machine code generator. So compiler design has changed considerably over the years. And if we're still on the subject of what's happening to compiler design, I think this is a fascinating area even now, because there are some very interesting experiments being done trying to use machine learning and AI techniques for producing compilers. As you know, with machine learning, you present a whole bunch of examples. And one of the most interesting developments that I've seen recently is people speak to their natural language processor, which then produces a compiler in some language like JavaScript or so on for creating computer games. So if you haven't seen any of these videos on producing compiler games using spoken language, computer games, by speaking what the game should do into machine language programming and natural language processing program, I suggest you look at them. It's intriguing, but whether they'll ever be able to produce compilers for the complexity of languages like C, C++, I don't know. I think that's an open question. And if you recall, way back many decades ago, a number of people proposed natural language as a programming language. And people pointed out that natural language is highly ambiguous, inherently ambiguous. And the last thing you want is a disagreement between the programmer and the compiler writer as to what the semantics of a programming language should mean.
Yeah, thank you, Al. Let me just mention that, what Al mentioned at the end, translating spoken words into a computer game. So that will be the topic of the opening keynote for the virtual workshop that's planned next week. Let's take a question from our remote participants. So I'll just read it for the benefit of everyone. So it's from Mike Hicks, and it says, your definition of computational thinking is intriguing and compilers illustrate it well. Is it possible to use language translators to teach computational thinking to non-computer scientists? What do you think?
Well, this is, again, a very important and intriguing question, because how do you teach people to think? In fact, I've been wondering how to do that for my entire life, because I've been very interested in how best to teach. And then one of the things that you should do in teaching is communicate to your students. And if you're in the business of producing software, what I have learned from a lot of experience is that it helps enormously if you do a little bit of thinking before you start programming. That may be old school, but thinking and then programming is a much better strategy than programming and then wondering, what the hell went wrong with my program? Now, as far as using programming language translators to teach computational thinking, I think that's a very good research area, because people are using computer games to try to teach computational thinking, and they seem to be popular in certain circles, that students like learning by solving puzzles or playing games more so than by reading. And what I've also noticed is that students have many different styles of learning. Some people are word-oriented and learn by reading. Some people are visually oriented and learn by seeing pictures or videos. So learning is very idiosyncratic. And what I found in when I was teaching, I would always use 2 or 3 different ways of trying to convey a concept, because the first way of expressing the concept may not resonate with the student, but the second or third way may be much better in getting the idea across. So repeat for learning is not a bad strategy, but repeat in different ways.
Thank you. Maybe one more question, and anyone in the audience, or we have questions online? Yeah. So this is from Nizari, and it says, what are main possible differences between pipeline of classical compilers and quantum computing compilers? Do researchers add or remove any specific phase to the classical phases of the compilers for the quantum computing compilers?
Designing compilers for quantum computers is, I mentioned, we can use the traditional techniques, but because of the no cloning theorem in quantum mechanics, your programming language for a quantum computer does not allow you to have a copy operation. You cannot copy the value of a variable. And the algorithms, and I suspect this will be the case for the foreseeable future, that there won't be a standalone quantum computer. There'll be hybrid classical computer, quantum computer systems. So Shor's algorithm has a lot of pre-processing done by a classical computer to reduce the factoring problem into a problem for computing the period of a function. And he uses the quantum computer to compute the period of a function using the operators that you can implement on a quantum computer. And then you get the result and then do some post-processing on your classical computer. So if you look at, I think all of the quantum computers on the market, they are controlled by classical computers. And the classical computer prepares the input to the quantum computer, and then the quantum computer essentially computes a unitary transform, does measurements, and returns classical bits to the classical computer that invoked the routine. So you can think of a quantum computer as an ASIC attached to a classical computer, except that the quantum computers that are built today are usually kept at very cold temperatures, like a few millikelvin. So chances are you won't have them in your iPhone or in your pocket anytime in the near future.
Okay, thank you. We do have some more questions, but unfortunately we have run out of time. So let's thank Al again for a great talk.
Thank you, everyone.